We're finally getting into the meat of the book, Stanovich's How to Think Straight About Psychology, and we're getting into how to manipulate variables and control conditions and create conditions in order to test our hypotheses or test variables that we think might be important in explaining whether it be human behavior or social conditions, living, and so on. And so we're getting into the properties that are important in experimental design. And following Stanovich's lead, we'll start off with a couple of word problems that you'll have to try to solve using mathematics, specifically physics. And so the first image here, imagine that you have a ball on a string and you are spinning it around your head. And so I've got this image here that I've kind of quickly sketched. And so you'll see the arrows indicate how the ball is traveling around. So you're spinning it for a while, and then the string is cut at the precise moment where the ball is in this picture. The question is, where does the ball go from there? How does the ball travel? What is its trajectory? Draw the sketch if you want, or just imagine how you see the ball moving once the string is cut. To solve this problem, you need to understand the physics of motion and then apply it in this real-world situation. A second word problem that's provided, again, I have a visual illustration here. Imagine you're flying this bomber jet. I apologize for the war context, but you're flying this bomber jet. Let's say you're just doing target practice, and you want to hit this target on the ground. You are at 20,000 feet. You are driving, or you're flying 500 miles per hour. Do you drop the bomb at point A so that the bomb will travel as it falls? Will you drop it at B because the bomb will fall directly below? Or will you drop it at C because the maybe wind resistance will cause it to drift behind you as you continue going, and that's how you hit the target. So do you drop it before the target, directly above the target, or after the target? Again, this requires basic physics of motion applied in this real-world situation. Now, those are simple questions. The next question is going to be a little bit more complicated. And by the way, pause the video, think about what your answers are to each of them. The whole purpose here for those first two physics problems is to show that applying mathematical reasoning to real-world situations is very simple. When we get into the same kind of scientific reasoning in psychological problems or to solve psychological problems, it is significantly more difficult because we don't think about psychological problems or psychological factors such as intelligence and development the same way we think about balls being swung around on strings. We don't have any personal relationships to those, but we all have a deeply personal relationship to psychological structures that make us who we are. So it's essential that we master the principles of scientific reasoning so that we can distance ourselves from the personal part of psychology. That way we can look at variables in psychology from an objective, careful, scientifically reasoned perspective. All right, so here is another example that comes from the textbook. This is a lot more complicated, and so I've drawn a diagram. The context is this. There was a cholera outbreak, and so tens of thousands of people in a community were dying of cholera every year. And community members wanted to know what was responsible, and so there were a lot of hypotheses. Some people thought it was people living in close conditions were passing it to one another and then becoming infected and dying. Others thought it was working conditions, so not even living conditions. This was working conditions. Maybe they're being overworked. Maybe it was who they come into contact as they're working. Maybe it was the materials that they're working with. Others thought it was some industrial waste that people were coming into contact with. Some thought it was from a water source, and so on. One of those hypotheses was the last one I mentioned, and that was infected water sources. And so there were multiple water plants that were supplying water to neighborhoods throughout the community, And the hypothesis was one of these plants was delivering infected water, or water that made its consumers more likely to develop cholera. And so, what I have here are two conditions that could be useful to compare the cholera outbreak. So, the cholera outbreak, people dying from cholera, would be the dependent variable, and which plant delivers the water would be the independent variable. So there's two conditions, condition A and condition B. And so in condition A, you'll see we've got plant A delivering water to neighborhoods A, to the houses in neighborhood A. So there's two clusters of 4 houses that represent neighborhood A. And then over here we've got plant B that delivers water to neighborhood B, as represented here by 2 clusters of 4 houses. Now, in this condition, we can compare the cholera outbreaks or deaths from neighborhood A to the deaths in neighborhood B, and that would show whether plant A was killing more people than plant B. Or if they were the same, we might suggest that the plant isn't responsible, because if they have the same numbers, it's probably not going to be the plant's fault. Now, over here in condition B, notice that plant A is delivering water to this cluster in neighborhood A, but this cluster in neighborhood B. So plant A isn't exclusively delivering water to neighborhood A, just part of neighborhood A, and then over here part of neighborhood B. Also, plant B is delivering water to part of neighborhood B and part of neighborhood A. So obviously this one's a little less tidy, because here all of them are A, over here all of them are B. And then over here plant A is divided and the neighborhoods are divided, but we get to compare neighborhood A and neighborhood B, all of whom get their water from plant A, and we get to compare neighborhood A and neighborhood B, all of whom get their water from plant B. So consider both of these setups, pause if you'd like, and examine which experimental condition, and by the way, this wouldn't be experimental, this would be a natural condition, because the researcher, the scientist, isn't the one determining who gets the water. They're not in control of that. But which represents the most naturally occurring control for us to understand whether or not the plants are responsible for cholera. So, decide. Let's move on. So here is the first condition, and these are approximations of the actual data that was collected in trying to determine whether or not the water plants are responsible. Plant A had 180 cholera deaths per 10,000 people. So a relatively small percentage, but any percentage would be terrible. Like, we don't want any percentage of inhabitants to die. Plant B had 140 cholera deaths per 10,000. Again, it's a very small number, but when we're talking about deaths of hundreds of people, no number is desirable. So, comparing plant A to plant B, it sort of looks like there's no difference. Plant A seems just as responsible as plant B, which means there probably isn't strong enough evidence to conclude that the water source is the responsible factor, or the responsible variable contributing to cholera deaths. Now, in scenario B, remember that's when we divided the neighborhoods up, and so each water plant delivered water to houses in both neighborhoods. We see something a little bit different. Plant A, which collected samples from neighborhood A and neighborhood B, had 315 deaths per 10,000, which is like twice as much as we saw in the previous data samples. And plant B had only 37 deaths per 10,000, so a significant drop in plant B deaths and a significant rise in plant A deaths. Obviously here it looks like plant A is responsible for cholera deaths, because suddenly we see a much stronger correlation between the neighborhoods it delivers to, or the houses it delivers water to, and cholera deaths. Now, why the sudden change in data? And note how in these examples we can imagine that plant A, or rather neighborhood A is, let's see, is the affluent neighborhood, and neighborhood B is poor neighborhood. The houses in neighborhood A may be $1 million a piece, and the houses in neighborhood B may be $50,000 a piece. Well, that sort of socioeconomic status can buy, that neighborhood A has, can buy a lot of health care. Perhaps they don't even drink water from the tap. And so, even though in this scenario, or in the first scenario, neighborhood A was only receiving water from plant A, they had the resources to fight it medically or to defend themselves. And so what we saw was a pretty even split between, so there were still more cholera deaths from plant A, even though these people had the resources to avoid medical conditions. And if we kept that into consideration, then we would think, wow, plant A must have a problem, but the data doesn't really show it. Plant B, by the way, which doesn't, in the second case, it's clear that it doesn't have contaminated water. The neighborhood wasn't very capable because of poverty. They weren't very capable of defending themselves against infection. So if they picked it up anywhere, they were more susceptible to dying. So the number 140 would be pretty alarming if we knew that the plant wasn't responsible. Clearly, there was something else to explain the incidence of cholera outbreaks. It was only when we controlled for socioeconomic status by drawing samples from both neighborhoods that we really got to see that plant A was significantly more responsible, or considerably more responsible for the deaths than plant B. Keep in mind that plant B here is delivering water to this neighborhood, or rather, plant B is safe, so it doesn't matter which neighborhood they're delivering it to. But over here, plant A, this neighborhood can defend themselves from the cholera, perhaps if they contract it. Over here, the citizens of neighborhood B, they cannot. What this real world study, this was a naturally occurring study, shows is that it is important that we control for any possibly confounding or confounding variables that might interrupt or interfere with the variables we're trying to test. And so if we're looking only at where water is coming from, we need to consider other possible explanations that may help us understand why a person who is contaminated ends up dying or actually contracting a severe version of the disease. So as scientists, we need to think through all possible explanations, all reasonable explanations, and then make an effort to control for those alternative explanations so that our results don't reflect these additional explanations. They only reflect the one explanation we're testing, which is our hypothesis. So in this example, it just so happened that there were naturally occurring conditions that allowed, the scientist's name was Snow, allowed Snow to test the hypothesis that water contamination was responsible for the cholera outbreaks and control for the impact, the factor of socioeconomic status. But scientists are seldom able to naturally control variables, which means they, or we, have to manipulate variables or create artificial conditions that allow us to isolate the one variable we're testing and then control all the other possible variables. So here are a couple of quotes from Stanovich. By comparing data patterns under different conditions, scientists rule out certain explanations and confirm others. And it is a consequence of the experimental design that allows them to do it. Second quote, the best experimental design is achieved when the scientist can manipulate the variable of interest and control all the other extraneous variables potentially affecting the situation. All right, so I've talked about a lot of concepts, and so let me go over some vocabulary. A variable, you'll recall, and this is Research Design 101, is in psychology, any empirical factor that might influence the subject of your investigation. So if you're interested in student achievement, sleep might be a variable. Studying might be a variable. Difficulty of the schedule might be a variable. Academic preparation could be a variable. IQ could be a variable. And so there are a variety of variables that could potentially impact the subject we're interested in, which in this hypothetical case is student success. And so variable is a big category. And within that category, we've got some other variables to talk about. One is the independent variable. If we're interested in testing a hypothesis, we're usually comparing the relationship between two variables. We might say, for example, that sleep, adequate sleep, is an important contributor to student success. Therefore, adequate sleep then would be the independent variable because I'm trying to test its relationship to the dependent variable, student success, which we might determine by GPA or measure by GPA. In order to test that, we need to take participants and subject them to different conditions, lots of sleep or adequate sleep, and inadequate sleep. And so those would be the two conditions. And since we're manipulating that, that's the independent variable. That's what we're changing. And then we're looking at the outcome, which would be GPA. Does their GPA change when we artificially manipulate their sleeping conditions? So that's an independent and dependent variable. In that condition, we would need to make sure that IQ isn't impacting the results of the study. We need to make sure that schedule difficulty isn't impacting the results of the study, and so on. So those in this example are potentially extraneous variables. So these are additional variables that all lead to student achievement. And so we need to make sure that those aren't affecting the one variable we are studying, which is adequate sleep. And so extraneous variables may get in the way. They're alternative explanations, but because they're just extraneous, hopefully we know they're important, but they're not impacting the results of our study. Now, confounding variables do impact the results of the study, and they're usually variables that we didn't think about, that by virtue of our experimental conditions, we're not just testing, in this hypothetical case, adequate sleep, but what sort of other things are attached to not sleeping enough? Maybe caffeine use? Is there a relationship between caffeine use and student success? Students who are getting inadequate sleep are more likely, probably, to use caffeine. So, but does caffeine have a performance enhancing effect when it comes to academics? Maybe. In that case, it's a confounding variable. And so we would need to control for caffeine consumption. What else might impact that? Inadequate sleep, maybe that gives me more time to study. So now the people who get less sleep are studying more. Is that going to impact the results of achievement? Possibly. And so there are a lot of potentially confounding variables that could interfere with our study. We would need to control as many of those as possible so that we're not measuring those instead of the independent variable that we've selected. The last two words, manipulation and control. Manipulation is what we do to the independent variable in order to test multiple conditions, and then the control itself is any steps that we make to limit the impact of extraneous and confounding variables. So, for example, if I said that everyone in the study, whether you're in the experimental condition with adequate sleep or the control condition with inadequate sleep, whichever setting you're in, you can only have 1 cup of coffee a day. So that would be my way of controlling for the caffeine consumption part, or you can't take any caffeine pills and so on. So we would artificially create conditions that would allow us to test the relationship exclusively between sleep, or adequate sleep, and student success. Now, how many college students would want to participate in that? Probably none. So let's go back to the first example, the first complex example. And this was the one that had the best naturally occurring control, where both neighborhoods were receiving water from both plants, which allowed us to allowed snow to control naturally for socioeconomic status and its impact on health and mortality. What possible spurious correlations? A spurious correlation is a relationship that we find, so the data would show that, there is a positive relationship, but the relationship isn't actually between the variables tested. It's a relationship between maybe one of the variables and some other variable we haven't thought of, and so it might appear to be an effect, but really what we're testing, what we found was some other effect that we don't know about yet. All right, when we're talking about control, the important factor here is that we control for all other possible explanations, and so we're only testing one independent variable. So there's not any other variables that could reasonably explain the results that we find. Here was a collection of studies that were found without a control group, with an okay control group, and with an actual control group. And the studies were on the effectiveness of the Portocaval shunt to treat cirrhosis of the liver. And then I think this was collected by some psychologists, Nisbet and somebody else, I forget their name. So of the studies that had no control group, doctors found that almost 97% of the studies showed that this Portocaval shunt was moderately effective. That's a big percentage. Moderately effective isn't great, but any amount of effectiveness, I think, would be desirable when we're talking about cirrhosis. In groups, or in studies that had a control group without random assignment, almost 87% of studies showed that the treatment was moderately effective. So less impressive, but again, this actually has a control group, which means that some people who wanted the treatment didn't receive it. And even though they didn't receive it, they probably improved. And so we can throw out 10% of the effect that we found with the experimental condition that did not have a control group. So that in that case, some of the findings in the first example, some of the findings where 97% of studies showed that the treatment was moderately effective. Some of them were spurious, so at least 10% of those were explained by something other than the treatment, because the control group got better even though they didn't receive any treatment. And then the final one, control group with random assignment. Only 25% of studies showed that treatment was moderately effective. So what's the difference between random assignment and non-random assignment? Well, look at it this way. With random assignment, say 50 people all have the condition, and these 50 people all want treatment. In the non-random assignment, the experimenter chooses who gets the experimental condition and who doesn't. So it might be the case that the first 50 people who applied get the treatment and the next 50 do not get the treatment. Well, then it wouldn't just be testing treatment versus non-treatment. It may also be testing in a confounding variable, the people who are more likely to seek treatment. And so people who are more conscientious, who are more responsible, who are on top of their scheduling. And so the treatment on top of a higher level of conscientiousness may lead to more effective treatment, and so conscientiousness isn't controlled with the non-random assignment. It could also be that the experimenter, we don't know this, the experimenter may have picked the 50 candidates who had the lowest levels of cirrhosis and included them in the study. People with higher levels of cirrhosis they did not include. We don't know that for sure because random assignment wasn't used. Random assignment means that everyone who applied all met the same conditions for application, and everyone had an equal chance of participating in the study. Now, when it was organized that way, which means any person at random could have been selected, which means there isn't any other variable that would predict why they were in the experimental condition versus the control condition. The only explanation was that they were randomly put there. The administrator of the test doesn't even know who was in which group, so there's no subtle "you're gonna get better" sort of communique that was given. And when that happened, only 25% of studies showed that treatment was moderately effective, which means in the first study with 97% moderately effective, almost 70% of that was a spurious effect. Now 97% is huge. That means almost everyone who does this treatment will get better, or will get moderately better, as opposed to 25%. So 70% of the impact was not explainable by the treatment itself. That's why random assignment is so important, but it is the hardest to set up because you, as the experimenter, have to be the one in control, assigning conditions and controlling variables. All right, this is another example that was given in the textbook. It doesn't matter what the treatment here is. Let's say it's SSRIs for the treatment of depression. In this data set, this raw data set, we can imagine that for patients who received treatment, 200 improved and 75 showed no improvement. So that was a sample of 275. Of the sample who did not, the participants who did not receive treatment, 50 improved and 15 showed no improvement. So looking only at this raw data and what we've talked about so far, was the treatment effective? So can you use this raw data to draw a conclusion about whether or not, by comparing the treatment versus non-treatment, the experimental versus control group, can you explain or conclude whether or not this treatment was effective? Now, most people looking at this, just like we'll go back to the physics examples earlier, we sort of have assumptions about the physical world, which may or may not be right. We'll look at those in a minute. Most people, most college students, when they look at this, they say 200 people got better. Well, that's a lot better than 50. Therefore, it must be really good. And 75 people showed no improvement. That's a lot, but look at how many people did receive treatment. So we can sort of forget about that. Only 50 people who didn't receive treatment got better. That's not a lot. And so it must, they definitely would have preferred to have received treatment. But to calculate this, we have to recognize that the sample who received treatment is much larger than the sample that is not. 275 versus 65. And so to calculate improvement, we would have to take 50 and divide it by 65, which, if I remember correctly, is about 76% of people who did not receive treatment got better. And over here, we would need to divide 200 by 275 to see the percentage of people who got treatment got better. And there, again, if I remember correctly, the percentage is about 72%, which means that a smaller percentage of people who got treatment actually had improvement, as opposed to 76% of people who did not receive any treatment got better. So this means that the treatment is not only ineffective, but it's actually probably harmful because a greater percentage of people who had treatment did not improve when compared to people who received no treatment. That's just statistics right there. All I did was calculate averages. All right, let's go back to some of those previous questions. College students tend to mistake what will happen when you let go of this string or when the string is cut. Most college students will predict that the ball will curve. Like when you let go, maybe it won't continue on the same line, but it will curve. It won't go straight. But what actually happens is where the ball is right now, it will go at a right angle to where the string is if you cut the string. It'll go at a tangent to the circle, and so it'll go in a straight line from where it's released, perpendicular to where the string currently is. In this next slide, you would have to, because you're moving at 50 miles per hour, when you drop the bomb is initially moving at, not 50, moving at 500 miles per hour. So you drop the bomb, and the bomb is initially moving at 500 miles per hour, but since the velocity is not being held constant, it'll start slowing down immediately, but it won't slow down to zero immediately. It'll have all the wind resistance that'll cause it to slow down as it falls. And so you would have to let it go before you reach it because the bomb itself will continue traveling forward on the same vector direction that you're flying in. If you dropped it at B, then the bomb would fall past the target, and if you dropped it at C, the bomb would drop well past the target. So you'd have to drop it at A. Now, the reason why that's included is because we encounter the physical world every moment of every day, but that doesn't mean that we think about it in a rational, logical and reasonable way. Even though it's not who we are, it's not the personal stuff of who we are. Psychology and sociology and the social sciences examine the personal parts of who we are, things that are very intimate to us. Uh, and all it makes it that much harder to think about these features of who we are in a logical, rational, and reasonable way. And so we have to be really careful about what we count as evidence and how we draw our conclusions. And that's what this whole book is about. That's what scientific reasoning in the social sciences is all about.